everyone. Thanks for coming. I'm Josh Goldberg. Just curious, who here has used TypeScript ESLint before? Anyone? A few? Awesome. Yeah, so I work on that. I'm a full-time open source maintainer in the TypeScript ecosystem. I focus on toolings such as TypeScript ESLint that lets you write code with more security, stability, confidence, stuff like that. Out of curiosity, anyone here read the book Learning TypeScript? One hand, two. Okay, well, I wrote it, and I'm a Microsoft MVP. Thank you for your support, everyone. But I'm not here to talk about any of that stuff. I'm here to talk about testing. Who here likes unit tests? Yes! The most exciting part of the development cycle, not when it hits users, not when you get to think of all the cool things you can do, but when you get to test it. I know. But seriously, I want to ask you all right now a real question. Please just shout out your answers. Why do we write unit tests? Punishment. I hear a punishment. What was that? Did you say something about suffering? Oh, yeah. So I heard a few good things. Also, my cursor's on the screen. I hate this. Every time there's like something wrong. Mac. Okay, well, we write unit tests to verify correctness and suffering. We prevent regressions in case the code might break in the future from changes. We make it easier to be able to run a specific part of code, such as under a unit test. We document how to use the thing. Unit tests might not be primarily for documentation, but they actually do a good job of it sometimes. I like unit tests. Now, let's take a look at a button. You don't have to write React or Solid or Preact or any of the possible UI libraries that this could be implemented in. But this button is a pretty reasonable thing. You might take in like an on click, and when it's pressed, you set this running, this on state, you await the on click, and then you set the state off. Now, you might write unit tests, a couple of quick ones for this button. You might say that if it's clicked, you should call on click, and then when it's clicked, you render ... And I don't have a code snippet for you, but I did write this locally, and these unit tests passed. How many bugs can you see in this code? The answer is not 0. I see bugs. And there are actually multiple bugs in this code, but the first big one we see is that this statement, the on, is wrong. When the button is on, that means click is happening, the on click is running, so your text should not be the click me text, it should be the ... Did anyone spot that? Because I gave you like 3 seconds to read the code? No. Unit tests are not infallible. It is entirely possible to have a fully tested application, 100% unit test coverage, woo, and have incredibly glaringly obvious in retrospect bugs. What a shock and horror that is, that you could test your code and it could still be wrong. They can easily miss functional bugs, and there are a few reasons. Mismatched async timings, which is why that was broken. We'll look at that in a moment. You might do an assertion that doesn't assert anything. More on that soon. You might miss an edge case, because there are a lot of edge cases in code. I don't know how many of you have been developers long enough to see an edge case or two, but trust me, we've all seen them. And lazy developers, which is a phrase I hate, by the way. Please don't use the phrase lazy. We're not lazy, we're hardworking, we're just rushed for time. So I say rushed developers is a phrase that makes me less unhappy. I am personally quite lazy, but that's besides the point. Now, let's look at each of those in order. Mismatched async timing. Let's say that your unit test renders the thing, sets it up, whatever you're doing in your code, clicks, and then asserts that there's a particular text on screen. Now, this bug here that we saw with the button having swapped on or off text, well, if you click and then don't await, or let's say that you click and it finishes too quickly, and then asserts, so you're asserting either before or after the button swaps a text, you might be asserting on the wrong thing. And this and all the other examples I'm going to show you are actual bugs I have seen in production, where someone wrote an assert that ran before the button changed or before the UI element updated, thereby not catching what it was supposed to catch. Bug. Horrible. Anyone here use testing library, any of its variants, testing library React? Does anyone want to guess what this does if no elements are found? Nothing. Thank you, yes, nothing. Testing library React is currently the most popular, at least one of the most tweeted about testing assertion libraries and DOM manipulators for React and similar. And it has a set of functions, get by text, query by text, find by text, and others. Get by text throws if nothing was found. Query by text returns null. I have seen tests that end with query by, and then they don't fail because nothing was found. It doesn't throw an exception, an error. Tests. Also, edge cases. What happens if you have an equality, a double or triple equal for the JavaScripties like me, and your unit test only tests above and below, it doesn't test equal? And let's say your behavior changes over time. Your test wouldn't catch that. You now no longer catch the right edge case of equality checks. And lastly, rushed developers. There are quite a few tests that if I were working with unlimited time and resources, I would probably have wanted to write on that button. I might have wanted to test that, let's say if you double click it, it doesn't call onClick twice, which is the other bug. The answer was at least 2. I can't say specifically 2 because there might be more bugs, but I can tell you at least 2 bugs. And you also maybe want to check that, okay, we've asserted what it renders normally, or we've asserted what it renders when clicked. What about all 3? So that's 3 different tests there. So these all come together to a phrase I've seen in pop culture: who watches the Watchmen? Or who tests our tests? How do we know that our tests are good? How do we know that they test what they're supposed to, that they're stable, that they run in a reasonable amount of time? Well, I can help you with one of those things. And in order to do that, I want to bring up an abstract syntax tree term. Who here has used ASTs before? Almost no one. The answer is all of you, because ASTs are how common tools such as linters and formatters work with your code. So before I show you things that help with tests, I want to dive in a little bit into how all this stuff works. An AST is a representation of your code. I'm going a little too fast. I'm going to take a little drink of water, slow down. When I'm at home, I have a little paper that says slow down above my webcam. Yeah. Someone has noticed I speak quickly. If we were to represent this call expression, as tooling might call it in TypeScript land, we might say that it consists of 2 things: a member expression, console log, and a literal, hi. And that member expression consists of the console and the log, so 2 identifiers as they're called in code. AST, or abstract syntax tree, refers to the idea of representing these things: call expression, member expression, identifier, literal. And they can often be represented in POJO, plain old JavaScript object form, or even JSON. This is the same thing you just saw on the last slide, but in programmatic representation. And if any of you are curious and want to play around with some ASTs, which I highly recommend, astexplorer.net, sorry I couldn't find the dark mode for it, just to keep it consistent with the other slides. I alternate personally. This has this great visualizer where you can type code on the left and select which language and which flavor of that language you want, and then see the AST on the right. So ASTs are cool, and they're used in a lot of different tools. Who here uses Prettier or dprint or any sort of code formatter? Awesome, you use this. A Prettier or AST cleanup, whatever, will take your code, turn it into the AST, and then print out the result of the AST, which means it will forget intentionally most of the formatting choices pre-AST. It's abstract, it's just the stuff, it's not the formatting concerns. And if you lint your code, for example, with my favorite linter, ESLint, woo, you might have something that looks at your AST, runs a query to find nodes that look a certain way, checks if the nodes are happy the way they're supposed to be, and then reports a complaint if not. Here we have a query: give me every member expression that's the child of a call expression. It's kind of like CSS queries. And then if the node is console.log, give the user that little angry red squiggle. Who here has received a red squiggle in their editor? Woo! Yeah, yeah, yeah. Most pained woos I've ever. All right. And I'm talking about mutation testing. So I'm going to define here: a mutation is a single change to the AST, which we will then test. We could, for example, figure out a bunch of different ways to test or to change our AST, to change our code. An example here that I roughly pulled from the Striker source, that's the library I'll soon show, is what if for every binary expression, which is roughly what this code selects on, we yield, function programming shenanigans, we yield a change where we get that same node but with a different operator. Like for example, you might take this is above 18 function and find 2 different versions of that function. And each of these versions is buggy. This is not the intent of the code as originally written. But if you were to somehow run all your unit tests on that function and see which of these mutations, if any, do or do not cause a failure, you could then pinpoint which potential areas of code are not actually covered by unit tests. So that's what we're going to do. We're going to introduce a tool called Striker, which will run a bunch of mutations, changes to your code, rerun the impacted unit tests, and then see which changes survived, which I think is really cute. I also think their branding is on point. I'm actually wearing Striker socks right now, if you can see. And the reason why it's called Striker is because it's named after the villain from X-Men who tried to kill all the mutants. Oops, that guy, which I just think the branding is cool. So I'm going to walk over here. You can get started on an existing project. I'm not going to show you that. Instead, I'm going to show you this fork of their example called Robo Cafe. We'll see if the demo gods smile upon me. Code Robo. It's so difficult. All right. So I'm going to, let's npm start here. All right. So we got, oh, you can see my GitHub notifications. That's not good. We got this cafe here where like I can order a cola, a boba tea, some stew, submit order, and order. Awesome. This is a sample app. And if I were to go back to the app and do npm run test, I would run all my unit tests, and we see we have the amazing, I loved seeing that solid green, 100% unit test coverage. Oh, there's my app also. Oops. And then if we open, what is it, reports, coverage, index, HTML, we can see 100% unit test coverage. By the way, for those who haven't used this before, a lot of unit test libraries will be able to generate an HTML rendering of like what things are or are not covered by how many unit tests. This total price getter here was covered by 5 or 6 unit tests. But now I'm going to run npm run test mutation. Let's zoom in a little bit, which is going to run Striker. And I'm going to just quickly go through some of the console output. It found 13 of 95 files to be mutated. There are 157 different potential mutations it could make. It will rerun unit tests, so it's running just, it says. A lot of progress. And we see 63 mutants survived. So that's not good. We wanted to kill all of them. And if we go down to past our tests, we see that actually it will output to us, these are potential bugs in our code, things that are not covered by unit tests. And this is wild to me every time I see it, that this 100% tested application, we just erased the contents of a function, just had it return undefined, and none of the tests failed. What the F? So if I actually, I'm just going to go straight to the mutation report. If I go to the really snazzy looking Striker report, we can see a similar thing, similar report to the test coverage. If we go to like the first red complaining place order component and go down to get total price, we see it's got some unhappies, that this total price getter survived despite having 4 tests cover it. So, you know, covering code in your test clearly is not enough to make sure the code works. And if we go down to the unit tests, which we see in the report, and open it in VS Code, we see that, I'm just going to fold all, it's actually got like a fairly comprehensive set of tests. But just to test things out, I'm going to, let's see, npm run just place order dot compone, whatever, watch. Just, do I have it? There we go. This is going to, oh my gosh. Well, whatever. Let's, I changed things in my system right before the talk. Let's just lol. So npm run test. So I've completely changed the contents of this function. It needs to return a number, so let's do 1337. There we go. So everything passed, even though I'm returning a clearly wrong total price. If I npm run start and go back, we see the total here is, in fact, 1337. Does anyone know what that stands for, what that means? Leet! Yes. So that's wild to me. And if you really want to get particular about it, you can like throw new error high just to see which tests, test singular. You can throw new error just to see which tests fail in your console. But again, you can also check the reports for that. So back to the slides. Here we go. Cool. So again, just to recap, 100% unit test coverage, 57.52% mutation test coverage. Wild. So what I just showed is a relatively new thing in modern development. I have yet to meet a team that actually does this stuff, which is unfortunate, but understandable. Mutation tests are really intense. They will find all sorts of things in your code. So I want to end in my last 12 minutes with a set of suggestions for how you might get started using this awesome thing. Mutation testing is just another piece of tooling. Whenever you have your product development lifecycle, it's a good idea to think, what are the things that you want to do throughout that lifecycle? All the different pieces of tooling or practices or behaviors that can prevent bugs. All of those tools have trade-offs. Mutation testing is awesome because it caught a pretty significant lack of unit test coverage. It caught that the total price getter just was ignored in unit tests, which means it can improve your unit test quality. It can pinpoint, these are the areas I should test more, in theory, if I wanted to get more coverage. But just show of hands, who here has greater than 95% unit test coverage? One person in the back with a hesitant hand. One really excited. Yeah, almost no one has the amount of unit testing that I would expect Stryker to be like really excited about. And every tool you add is a new barrier to entry. Every tool is a, a thing for new people to the team to learn. It adds to your CI times. It adds to your install times. It's something else for you, a chore. So my recommendation would be, if you have some amount of unit test coverage and you're happy with your tests so far, consider running Stryker once. Just get it running in like a fork, a branch, whatever, and then set up a hangout, a team meeting, whatever equivalent for you, and see, is this finding things that we actually care about? Is it showing us places where we have a gap in unit test coverage that we don't want to have a gap around? And if you really like what you see, you could run it in CI. It does have a mode where you can have it fail on any surviving mutants. You can also script it to fail if there's a threshold of mutants or some such. Again, I've yet to see a team actually do this, but I think it's a good idea. It's one part of what I like to call the bug acquisition funnel. Who here has used user acquisition funnel in their day-to-day life ever? The user researchy people. It's the idea that whenever someone enters your app, there's a funnel they go through to become a full using member or user. And there are drop-off points everywhere on that funnel. When you first visit the site, does it load fast enough? Is the call to action button prominent enough? Does the text convince you to click it, and so on? And bugs go through a similar idea, a similar process, where at the very beginning of your life cycle for a product, or at the very beginning of when you start iterating on a feature, you have all sorts of potential bugs. And as you go through your product life cycle, you narrow down which bugs might happen. The things at the bottom, I'll just get them all in order so it's easier to read. There's prior thought, which I'm going to go through each of these in order and just explain why I think they're awesome. Prior thought is designing the feature with intention. Thinking, how is this going to evolve? How do we adjust the architecture to support it? And how do we write it in a way that's stable? How do we give ourselves enough time to write it? Then you have static analysis, the area I personally play in the most. Things like type checking, linting, even formatting to help keep consistent code and reduce development costs spent typing out your spaces and tabs. Then you have dynamic analysis, unit tests, end-to-end tests, and now also mutation tests. But after that, there's still more that could be done. There's peer review, pull requests. There's telemetry, once the thing is in front of users, seeing do you have crashes reported in New Relic, Sentry, and so on. And then there's user feedback. User feedback's real important. Do real users actually enjoy using your product? Can they physically? All of these are really key parts of your funnel, and mutation testing is just one potential thing to do in there. So let's recap. A lot of stuff we covered. Unit tests, they are awesome. They can catch bugs. I like them. But they don't catch everything, and they are not infallible. It's entirely possible to mess up your unit tests. We introduced mutation testing, the art of finding all these different ways that we could modify the AST of code, and then the potential bugs that could come out of them. We should rerun unit tests to see if there are any. We talked about Striker, getting started using it, quick little demo app, and then how to integrate it into a team. Now, all of the things that I showed are available online. Striker Mutator is an open source project. It has JavaScript, TypeScript, .NET, Scala bindings. I know this is a big Scala shop here. JS and .NET, not so much. ASTExplorer.net is really great. And then I also want to give a shout out to Nico Janssen, one of the core maintainers of Striker, who's just a cool person, and gave me my Striker socks. He did not know I was going to mention him until today. Oh, you have a different opinion? Great. Rowdy knows, Nico. Cool. I also want to give a quick shout out to TypeScript ESLint, which is the main open source project that I work on. It will lint your code, as in it gets ESLint and Prettier working for TypeScript. And also, if you want to buy my book, Learning TypeScript, I'm a full-time open source maintainer, and this is where I get a lot of my money to do that. So that's all. Thank you very much, everyone.